Hi, and welcome to this lecture about computational graphs. Before we begin, let's start with understanding what are derivatives. Derivatives is a fancy word for a change in slope value. For example, if the value here is x, and that corresponds to a value of y, if we would change the value from x1 to x2 in this direction, what is the corresponding change in the y-axis? One can simply draw a triangle and put this as height and this as width, and basically the height over width is going to give you the derivative. Now what's special about this graph is the change from x1 to x2 will always be the same in terms of ratio when the change is to x3. So let's just extend this by a little bit. Let's pretend that's a straight line. And if x3 goes up here, and it goes right here, which is y3, so the difference in change here, in terms of ratio, will also be reflected here. And the reason is this is a straight line. Now let's look at a different example. And this one has the values plotted, so it will be perhaps easier to demonstrate. The line here is more curvy. So if we look at the value of 0 here, and let's say that's x0, so we see that when x is 0, y is 1. If we were to move 1 in that direction, so that x1 equals to 1, we would see that the value of y becomes 2. So therefore the change here was 1. But if we were to move 1 in this direction and call it x2, we would see that the value of y has now become 4. So the change here is now 2. Let's take another example. If we were to move 1 more in this direction and move up, we would see now the change to 8 is actually 4. So the change here has went from 1 to 2 to 4, although x has remained constant. The change in x has remained constant, but the change in y has exponentially increased. While in the previous graph, the change in x remained constant, so the change in y also remained constant. Not necessarily the same value, but the ratio has changed. And this is basically derivatives, is calculating this change in the graph functions. So let us hold this thought of what derivatives are for a minute, and let's talk about computational graphs and try to tie both these concepts together. So if you remember from the previous lecture, and this is a quick recap of logistic regression, x is your input value, and b and w are to be calculated in order to get the z value. The z value is confined in a sigmoid, and this basically gives us the y hat, which is the value we think is closest to y based on the w and b value. The sigmoid of z was also written this way. So this is the exponential, the sigmoid function. For the sake of this lecture, we're going to consider y hat as a, because we're going to do some derivatives. So instead of, this is just to simplify things. So the difference between y hat, or in this case a and y, was calculated using this loss function here. And remember, the loss function is calculating the difference between your a and y in a single data point, while the cost function calculates it over your whole training set, the average of over the whole training set. So let us take an example to try to combine these derivatives with computational graphs. So let's take an example that an input has two parameters. In lecture 1, we spoke about iPhones. So for example, storage space and any cracks. So let's just take that for an example. We're going to model them as x1 and x2. And according to the equation up here, this comes with a w1 and a w2. So it's x if we would think about it, is x1 times w1 and then x2 times w2 and so forth. And then we add that to v. By combining all of these together, z will equal w1 times x1 plus w2 times x2 plus b. And the output of this equation then goes into the sigmoid function right here, which we wrote it as that way. So minus z up here is this z right there. So we take the input that, and then we get the new value a. And then the output of this equation then becomes the loss function, which is a and y. So what we've literally done here is we've taken some input values. So this has been given to us, and this we randomly initialized, and we've passed it through these equations in order to get to our loss function and compare it with the y value we already have. So going from left to right, this is known as forward propagation. And the idea of the computation graph is to basically organize the computation of a specific function. So what we can see here that this happens first, then this happens second, and this happens third if we look at it from left to right. And this is known as the forward propagation, which basically calculates the output of the network. So at the end here, we're going to have some sort of value, which is the difference between these two, for example. Now, what is backward propagation? Backward propagation calculates the gradient using the derivative, and that's what we have introduced in the previous lecture. So, and this we'll explain this a bit more in the next slide. But basically, backward propagation goes from right to left, and it looks like if I change the value of a, how much will it affect here? If I change the value of z, how much will this be affected? And if I change the value of w2, how much will z be affected? It's basically calculating the derivative, which is the difference. So in the previous in the previous slide, we've shown that if x1 changes to x2, how much does that correspond to the y value? And it will be the same in this case. If a would change to a different value, how much will the loss function change? And by changing this, by understanding how this works, we will be able to get the value of a as close as possible to the actual value. A, again, is the value we predicted. So let's start on a clean slide here and try to explain backward propagation better. So again, we see the computational graph of this function, and let's start from the furthest right. So from the previous slide and from the previous lectures, we have shown that the loss function is calculated using the following. So we want to understand if dA were to change, how much would that affect the d function? So if this value were to change, what is the consequences it will have on the loss function? And to know that, we calculate the derivative. So basically, the minus comes down as a minus, the y comes down as a y, and the log of a, according to the calculus rules, just becomes a. The plus comes down as is, so there's 1 minus y, and then the calculus rule for this is 1 minus a. So what we see here is the derivative of this function right here. So if I want to know how much a affects the loss, I do this calculation, and I'm going to post a link, or let's hold on to that thought a little bit. So yeah, this is the calculation for the dA in the change of dL. Now, what about this point here? How much does dz have an effect on dA? So then we simply also write the equation dA over dz, which again, this is basically saying, this is a fancy representation of if the value of z changes, how much is that going to affect the a value? Where in this slide here, if the value of a changes, how much will it affect the loss function? So dA over dz, and I'm going to post the proof for this in a link, is basically a 1 minus a. So that's the derivative of this equation right here. Sorry about that. That's the derivative of the equation right here. So now we have this side. So let's just highlight this in the box, and let's highlight this in the box. And now let's go one more step backwards. So we're literally doing the back propagation. So x1 and x2 are given, so this is not something we worry about. But we do want to calculate the w1, the w2, and the b. Let's take dw1 an example. So we would like to know how much does dz change in relation to dw1. And if we look at this and apply the rules of calculus, this is the output of this is going to be simply x1. If we look at dz dw2, the output is simply going to be x2. And if you want to know why, so basically, if we are looking at this equation from the point of w1, this gets down to 0, and this goes down to 0, and this gets down to 1. So basically what remains is this, which is this value here. And when we do it in relation to w2, then all of this gets cancelled again, and this gets down to 1, and this remains, and this goes down to 0. And then if we look at the change of dB in relation to dz, then it will simply be 1, as b just goes down to 1, and everything else goes to 0. So what are we looking at here is a set of equations that will lead us to the end here. So if we want to now know, if I change the value of dw1, how is that going to affect my cost function? And that is simply by saying dl over dw1. And we have seen that dw1 has an effect on z by the following equation. So we just simply see that dw1 has an effect on dc, so that's going through this side. And now if we want to go in this side here, the equation is dA over dz, and if we want to go to this side, the equation is dl over dA. And what we see here is actually what we have down here, which is the chain rule. So if w1 would change, how much would that affect our loss function? And to do that, we calculate it using this way. So we simply substitute this by x1, and we simply substitute this by a1 minus a, and we simply substitute this by the following formula. I'm just not going to write it down. And the same applies for this here, and the same applies for that. So then we end up with the derivative of the w1 in relation to the d loss. So what do we do? So what do we do with this? And if you remember from the previous lecture, we have calculated that we needed W and B to be done this way, but this was for J, which was for the cost function, which is the average across the whole data set. While in the previous slide, we calculated for the single data point, which is for the loss function. So to rewrite this, we just add W1, so W1 minus the alpha for dl over dw1, and same for w2, d over w2, and the same for dA. So yeah, that's it. So this is for the loss function for a single point, while this is for the cost function, which is the average error across your whole data set. Thank you. If you have any questions, please post it below. Otherwise, don't forget to like and subscribe.